Imagine standing at the edge of a cliff, looking up at an enemy you cannot reach. You can see them. You can hear them. The drone of their engines rolls down through the cold air like a constant mechanical verdict. But every time you try to climb, the air itself stops you. Your lungs burn, your legs give out, your instrument needles drop into the red, and the enemy keeps flying higher, untouchable, methodical, and certain of their own safety. By the winter of 1944, that was the reality for every German fighter pilot strapped into a cockpit and scrambled into the freezing sky over the Reich. The enemy wasn't just winning. They were winning from a place the Germans could not follow. They had found a ceiling that no Focke-Wulf, no Messerschmitt, no emergency modification program could punch through, and it was killing Germany's air defense system from the inside out, not by destroying aircraft in combat, but by rendering them irrelevant. And somewhere in a design office buried deep inside a country that was running out of time, one engineer had already figured out why. His name was Kurt Tank, and he was about to build the most technically advanced piston engine fighter aircraft the world had ever seen. He had been working toward this moment for 2 years, watching the problem develop with the calm attention of a man who had trained himself never to look away from an inconvenient fact. To understand what Kurt Tank was trying to solve, you have to understand the invisible ceiling that was strangling Germany's air force. For the first years of the war, the Luftwaffe had dominated European skies. Their pilots were skilled, their tactics aggressive, their machines refined through years of combat experience in Spain and Poland. The Focke-Wulf 190 had arrived in 1941 and genuinely shocked the Royal Air Force. It was faster, tougher, and more heavily armed than anything the British had flying. Even the Spitfire pilots had to respect it. But the war had a way of accelerating everything. By 1943, the Americans had arrived in numbers, not in ones and twos, but in waves. Formations of hundreds of Boeing B-17 Flying Fortresses and consolidated B-24 Liberators, escorted first by short-range Thunderbolts, then by Mustangs that could fly all the way from England to Berlin and back. The daylight bombing campaign had become a relentless industrial grinder, and Germany was the material being ground. German fighter pilots fought bravely. They flew multiple sorties per day. They took staggering casualties. But a more ominous problem was forming high above them, one that no amount of courage or skill could solve. The Allied bombers were flying higher. At first, the ceiling was around 25,000 feet, then 27,000, then 30,000. And above 30,000 feet, the performance of every German fighter aircraft began to fall apart in ways that were not tactical but physical. Here is the engineering reality of flight at extreme altitude. The atmosphere does not end cleanly, it thins gradually, and as it thins, the density of air decreases. For a piston engine, which depends entirely on compressing an air-fuel mixture to generate power, this thinning is catastrophic. Above 20,000 feet, the engine begins to lose power dramatically. The superchargers that compress the intake air struggle to keep up. The piston rings lose their seal. Combustion becomes uneven, the mixture running lean and ragged. An engine that generates 1,800 horsepower at sea level might deliver 800 horsepower at 35,000 feet. The fighter that was deadly below the clouds became sluggish and slow above them. The propeller suffered too. In thin air, the same blade angle that drove a fighter at 380 miles per hour at 15,000 feet might only generate 280 miles per hour at 38,000 feet. The speed dropped. The climb rate dropped. The maneuverability dropped. The German pilot was fighting with one hand tied behind his back, and the hand doing the tying was physics. There was another dimension to this problem. The pilot himself. At extreme altitudes, the cockpit temperature dropped to minus 50 degrees Celsius and below. Pressurization systems in German fighters were crude or non-existent. Pilots wore bulky oxygen masks and heavy suits that restricted movement and reduced sensitivity on the controls. A dogfight at 40,000 feet was not the same as one at 15,000. A man could black out from a too aggressive turn, or lose the feeling in his hands mid-maneuver. By January of 1945, the situation had become critical. Reports were filtering back from the Pacific Theatre about the Boeing B-29 Superfortress, a bomber that had been specifically designed to operate above 40,000 feet. The Americans had built a weapon that flew in airspace where no existing German fighter could function effectively. if large numbers of B-29s were redirected to the European theatre, or if Allied air commanders simply pushed their existing bombers to operate consistently at ceiling altitude, Germany's entire fighter defence network would become useless. Kurt Tank had seen this coming. He had been seeing it for 2 years. Tank was not a typical wartime engineer scrambling to fix a problem after it appeared. He was the type of man who read the direction of the wind long before it changed. Born in 1908 in Bromberg, then part of the German Empire, where Tank had fallen in love with flight as a teenager. He was methodical, technically precise, and possessed of a rare quality among engineers of his era. He was also an accomplished pilot. He tested his own aircraft. He did not design from behind a desk alone. He climbed into the cockpit, felt what the machine was doing, and then went back to the drawing board with information that no instrument could have given him. By the time Tank joined Focke-Wulf in 1931, he had already established a reputation as a man who thought in systems, not components. He didn't just ask whether an engine was powerful. He asked whether the airframe could exploit that power. He didn't just ask whether a wing generated lift. He asked whether the pilot could actually control that lift in a combat environment. When he designed the Focke-Wulf 190, he made decisions that looked unconventional to outsiders, but were the product of precise thinking. He chose the BMW 801 radial engine not because it was fashionable, but because its wide frontal area, while creating drag, allowed for simpler cowling and better cooling, a practical advantage that paid off in the harsh conditions of the Eastern Front. Tank was an engineer who thought like a soldier, and a soldier who thought like an engineer. When the altitude problem began to sharpen, Tank did not wait for an official directive. He began conceptualizing a new aircraft, one that would be built from the ground up around a single question. What does a fighter aircraft need to be effective at 40,000 feet? The answer to that question required abandoning almost everything that made the Focke-Wulf 190 so successful at lower altitudes. At high altitude, drag was less of a problem because the air was thinner. This meant that a longer, more slender wing, the type that would be a liability in a turning engagement at 15,000 feet, became an asset. Longer wings generated more lift per square foot in thin air. They allowed the aircraft to maintain its aerodynamic efficiency, where shorter wings simply lost grip and began to wallow. Tank designed the TR-152H, the H standing for Hawk, meaning high altitude, with a wingspan of 47 feet and 4 inches. That was roughly 10 feet wider than the standard Focke-Wulf 190. On the ground, parked next to its predecessor, the TAR-152H looked almost ungainly. Too long, too narrow, with a delicate, almost sailplane-like quality that seemed at odds with a fighter aircraft. That appearance was entirely intentional. The fuselage was stretched by nearly 2 feet compared to earlier Focke-Wulf designs. This gave the aircraft a sleeker profile and improved its longitudinal stability at high speed, where aerodynamic forces could become violent and unpredictable. The tail surfaces were enlarged to match, giving the pilot authority over the aircraft even when control surface effectiveness dropped in the thin upper atmosphere. But the wing and airframe were only half the equation. The engine was the heart of the problem, and the engine Kurt Tank chose was the Junkers Jumo 213E. The Jumo 213E was a 12-cylinder liquid-cooled engine of considerable sophistication. In its basic form, the 213 series generated around 1,750 horsepower at lower altitudes. But what made the 213E exceptional was its supercharging arrangement. Most German fighter engines of the era used a single-stage supercharger. Some used a 2-stage unit. The Jumo 213E used a 3-stage supercharger system, an intercooled, high-pressure arrangement that compressed the intake air in 3 successive stages before delivering it to the cylinders. Each compression stage increased the density of the air charge. More air meant more fuel could be burned. More fuel meant more power, and crucially each stage operated efficiently across a different altitude band, so the total system maintained reasonable power output far higher than any single-stage system could manage. At 40,000 feet, a height where most piston engines were simply dying, the Jumo 213E could still deliver 1,750 horsepower. That was not peak power, that was cruise power, that was the power available for combat. To put that in perspective, the Rolls-Royce Merlin engine powering the North American P-51D Mustang, the best Allied fighter in the European theatre at the time, produced approximately 1,500 horsepower at its rated altitude ceiling, which was considerably lower. Above 25,000 feet, the Mustang's engine began to lose output. Above 30,000, the gap became significant. Above 35,000 feet, the TAR-152H would have been in a completely different performance envelope. Tank did not stop at the engine. The cockpit of the TAR-152H was pressurized, not the crude, helmet-dependent pressurization that left German pilots shivering and barely functional in their cockpits, but a genuine pressurized cabin sealed against the outside atmosphere. The pilots sat in an environment equivalent to approximately 26,000 feet, even when the aircraft was flying at 40,000. His blood did not boil. His hands did not go numb. He could think clearly, react quickly, and fight as effectively at extreme altitude as he could at sea level. This was not a small detail. It was a fundamental redefinition of what the pilot could actually do in that environment. The aircraft was also equipped with a MW-50 methanol-water injection system. When a pilot needed a sudden burst of speed, in the critical opening seconds of an engagement, or to escape a situation that had turned bad, he could activate the injection system. Methanol and water sprayed directly into the supercharger intake, cooling the compressed air charge dramatically. This allowed the engine to run at a higher boost pressure without detonating, for approximately 10 minutes. The TAR-152H could access an emergency power setting that pushed output to around 2,250 horsepower, enough to generate speeds the Allied fighters at altitude simply could not match. The armament was considered carefully too. Tank knew that a high-altitude interceptor would face specific targeting challenges. Closing speeds at extreme altitude were enormous. The time in which the pilot could fire and score hits was measured in fractions of a second. He armed the TAR-152H with one 30mm motor cannon cannon, firing through the propeller hub, and two 20mm cannons in the wing roots. The 30mm weapon was devastating. A single burst from a 30mm cannon could destroy a bomber. By the autumn of 1944, the prototype was ready for testing. It was January 22nd. 1945, when Kurt Tank decided the situation called for something more than instruments and telemetry. He climbed into the cockpit himself. There were test pilots available. There was a protocol. But Tank was the kind of engineer who believed that no piece of data was more reliable than his own hands on the controls. He had flown the Focke-Wulf 190 before it went into production. He had flown earlier TAR-152 variants during their development phase. So he was not doing this for show. He was doing it because he trusted himself more than any instrument panel. The aircraft lifted from the runway at the Focke-Wulf test facility and began to climb. Not the shallow, laboured climb of an aircraft struggling against physics, but a sustained, powerful ascent that ate altitude the way a good aircraft eats distance. 30,000 feet, 35, 38. And then, where other aircraft had always begun to falter, where the air had always grown too thin, and the engines had always begun to choke and die, the TAR-152H kept climbing, 41,000 feet. Tank levelled off and noted the aircraft's behaviour. It was stable. It was responsive. The pressurized cockpit was holding. He could feel the controls with the same sensitivity he would have had at 10,000 feet. The engine was running cleanly, the supercharger stages doing exactly what they had been designed to do, was feeding dense compressed air into cylinders that refused to acknowledge how high they were. He pushed the throttle forward and checked the airspeed indicator. At 41,000 feet, the TAR-152H was exceeding 470 miles per hour in level flight. The best Allied fighters at that altitude were pushing around 405 miles per hour under ideal conditions. That 65 mile per hour advantage was not modest. In air combat, speed is life. Speed buys the initiative. Speed decides who gets to choose the terms of engagement and who is forced to react. The aircraft that is faster can close, fire, and disengage before the opponent has completed a single defensive maneuver. Tank brought the aircraft down and walked into the debriefing room with the quiet confidence of a man who had just proven a theorem. The T-152H worked, not approximately, not partially. It worked completely, exactly as designed, at an altitude where the Luftwaffe had previously been helpless. News of the test spread through the German aviation establishment with a peculiar mix of elation and despair that characterized so much of Germany's technical achievement in the last year of the war. The engineers celebrated because they had done the impossible. The generals despaired because they knew what the numbers at the production office looked like. Germany in January of 1945 was not the Germany of 1940. It was a nation being compressed from every direction simultaneously. Allied bombers had spent 3 years systematically destroying factories, rail lines, fuel depots, and refineries. The transportation network was fractured. Raw material deliveries were unreliable. The workers who had once operated the production lines had been conscripted into an army that was running out of men to fill its positions. The Jumo 213E engine, as sophisticated and powerful as it was, required skilled machinists and precise tolerances to build correctly. A 3-stage supercharger is not a simple mechanism. Each stage uses a different compressor wheel, different intercooling arrangements, different pressure ratios tuned to a specific altitude band. Building it under factory conditions in peacetime required care and equipment. Building it under Allied bombing raids, whole with interrupted supply chains and a shrinking pool of trained workers, required something close to a miracle. The pressurized cockpit system required high-quality seals, gaskets, and precision-fitted glazing. The MW-50 injection system required clean methanol supplies that Germany was increasingly struggling to provide. The aircraft itself, with its longer fuselage and wider wing, was more complex to assemble than the standard Focke-Wulf 190. Every advantage the Tu-152H had over its competition came with a production cost attached. The first operational examples reached Jagdgeschwader 44 in early 1945, one of the most celebrated fighter units Germany had produced, led by legendary aces including Adolf Galland, who had already spent months fighting his own leadership over the deployment of jet aircraft. Initial deliveries were painfully slow, 10 aircraft, 20. Some units waited weeks between individual deliveries, watching the skies fill with Allied formations that grew larger and less afraid with each passing month. By March, perhaps 60 operational machines were in service across the entire Luftwaffe. By April of 1945, total production had reached approximately 150 aircraft, against an original requirement of several hundred per month. 150 aircraft. In the same period, American factories were producing over 3,000 P-51 Mustangs and P-47 Thunderbolts per month. British factories were turning out Spitfires, Tempests, and Typhoons at comparable rates. The Soviet Air Force, supplied in part by American Lend-Lease and rebuilding its own industrial base with ferocious determination, was fielding thousands of Yaks and La-Series fighters per month on the Eastern Front. The Tu-152H was not going to change that arithmetic. The pilots who flew the aircraft in combat reported remarkable things. In engagements where the TR-152H met Allied fighters at altitude, the German machine consistently held the initiative. Its rate of climb above 30,000 feet was unlike anything the Allies had encountered in a piston-engine aircraft. Pilots described it as commanding, a word that meant something specific in combat flying. It meant the aircraft responded before you fully formed the thought. Lol, it meant the controls had weight and precision, rather than the vagueness that crept into fighter handling at altitude. On several recorded occasions, pilots used the MW-50 boost to outrun American fighters that had every advantage of position and surprise. There is at least one well-documented instance where Kurt Tank himself, flying a TR-152H on a routine transfer flight, was bounced by a group of Soviet fighters. He activated the methanol-water injection, pushed the throttle to emergency power, and simply flew away from them. Not in a gradual, anxious separation, but in a clean, definitive sprint that left the pursuers behind before they could close to firing range. The aircraft was everything Tank had promised, but the men flying it against Allied formations were doing arithmetic of their own. 150 Tu-152H fighters against thousands of Allied aircraft meant that even perfect individual performance could not shift the campaign. A pilot who shot down 3 Allied aircraft before being outnumbered on the 4th engagement had improved the German kill ratio without changing the strategic position by a single degree. There is a particular kind of tragedy in technological achievement that arrives too late. It is not the tragedy of failure. Failure is simple. You try something, it does not work. You accept the result and move on. The tragedy of the Tu-152H was more painful because it was a success. The engineering was correct. The concept was correct. The aircraft flew exactly as designed and performed exactly as promised. The problem was external to the machine entirely. Germany's fuel situation had become catastrophic by late 1944. Allied bombing of synthetic oil plants and natural refineries had cut aviation fuel production by over 80% from its peak. Pilots who had aircraft to fly sometimes could not fly them because the fuel was not available. The T-152H's Jumo 213E, for all its sophistication, required high-octane aviation fuel, the same C3 fuel standard used by other high-performance German engines, and that fuel was becoming impossible to source in adequate quantities. Some units reported flying combat missions with degraded fuel blends that reduced engine performance significantly and increased the risk of detonation. A supercharger system calibrated for high-octane fuel, running on a compromised blend, did not deliver its rated power. The technical specifications assumed a supply chain that no longer existed. There was also the question of pilot experience. By 1945, Germany's pool of experienced fighter pilots had been depleted by 5 years of attritional combat on multiple fronts. The men being assigned to fly the TR-152H were often not the aces for whom the aircraft had been optimized. They were young pilots with limited hours, sometimes fewer than 100 total flying hours before they were assigned to a frontline unit, confronted with an aircraft that had demanding handling characteristics at low speeds and on takeoff. The long wing that was an asset at 40,000 feet was a liability on a short, damaged runway in winter conditions. The stretched fuselage required precise rudder inputs on takeoff that an inexperienced pilot might misjudge in the critical seconds before reaching flying speed. Several Tu-152H aircraft were lost not to enemy action, but to accidents during takeoff and landing, a brutal but predictable result of fielding a complex high-altitude specialist to pilots who had trained on simpler machines and had been given far too little time to master something new. Kurt Tank watched all of this from an increasingly difficult position. He was simultaneously the man who had delivered Germany's best fighter and the man who understood, with an engineer's unflinching honesty, exactly why it could not change the outcome. He had solved the altitude problem. He had built the aircraft. He had flown it to 41,000 feet with his own hands. The war did not care. There is a concept in engineering known as the system boundary. It means that the performance of a component can only be evaluated within the context of the system it belongs to. A perfect carburetor does nothing useful attached to an engine with a cracked block. A perfect engine does nothing useful in an airframe without fuel. A perfect aircraft does nothing useful when the infrastructure needed to deploy it, supply it, and crew it has been destroyed. Kurt Tank had built the perfect component, but the system it was supposed to belong to had already been dismantled by Allied bombers and Russian artillery. The Reich collapsed in May of 1945. Tank spent the immediate post-war years in Germany before relocating to Argentina in 1947, where the Peronist government was attempting to build a national aviation industry. He designed the Pulky II, a swept-wing jet fighter that flew in 1950 and made Argentina one of the few countries in the world to design and fly its own jet aircraft in the immediate post-war period. It was a remarkable achievement that received almost none of the recognition it deserved. Tank then moved to India in the 1950s, working for Hindustan Aircraft Limited on what became the Marut fighter bomber, India's first domestically produced jet combat aircraft. He was, in every phase of his career, the same man. Methodical, technically rigorous, willing to fly what he built, and invariably operating slightly ahead of the circumstances that surrounded him. The Tu-152H itself survived in tiny numbers. Today, only one complete airframe exists in the world. It sits in the collection of the National Air and Space Museum in Washington, restored to the condition it would have worn at the peak of its brief operational career. Its long wings still suggest the altitude for which it was built, the proportions slightly wrong by the standards of a conventional fighter, too elongated, too graceful for a combat aircraft, built for a different sky than the one that surrounds it. The Jumo engine sits quiet behind a polished cowling that once fed compressed air through 3 supercharger stages at 41,000 feet. Ground crews and restorers have noted the quality of its construction even in the late war period, evidence of craftsmen who took pride in their work even as the country around them was collapsing. It is a strange kind of monument, a machine that was never given the environment in which it could have mattered. What the Tu-152H represents in aviation history is not merely a German aircraft or a World War II relic. It is a case study in the relationship between engineering genius and industrial capacity. Kurt Tank solved every problem he was given. He designed an aircraft that could reach altitudes no Allied fighter could match, maintain combat speed in airspace where its opponents became sluggish and unreliable, and absorb battle damage with the toughness that came from Focke-Wulf's hard-won experience on the Eastern Front. None of that was enough, because wars at the industrial scale Germany was fighting in 1945 are not decided by the performance of individual aircraft. They are decided by the monthly output of factories in Detroit and Birmingham and the Ural Mountains. They are decided by the fuel depots that are still standing and the supply routes that are still open. They are decided by the number of trained pilots who climbed into cockpits that morning, and the number who will climb into cockpits the following morning and the morning after that. Kurt Tank understood this better than perhaps any other engineer in Germany's aviation establishment. He was not a propagandist. He did not make promises he knew to be false. He did not stand at a podium and announce that a single aircraft would reverse the tide of a war that had already turned against the nation that built it. He simply kept working, kept building, kept flying, because that was the only thing an engineer could do when the problem in front of him was real and the tools in his hands were equal to it. The altitude trap that strangled the Luftwaffe in 1945 was solved by one man with a drawing board, an extraordinary engine, and a willingness to fly the proof himself. The solution was real, the aircraft was brilliant, and in the end, it arrived the way all perfect solutions to already decided problems arrive, exactly on time to prove what might have been.